Hi, I'm covering section 3.5, the first part. I'm going to do this section in 2 videos. So I'm doing the first part today. We talked about polynomial functions in the last 2 chapters, or the last 2 sections, 3.3 and 3.4. And now that we talked about polynomials, we're ready to talk about rational functions. So a rational function will be the quotient of 2 polynomials. A function of the form f of x equals p of x over q of x, where p and q are polynomial functions, and q is not a zero polynomial, is a rational function. Okay, so examples. The following are examples of rational functions. Okay, well, any polynomial is a rational function where the denominator is a polynomial, is a constant polynomial. But non-trivial rational functions, that is, rational functions that are not polynomials, could be functions like 1 over x. Another one could be x plus 3 over x squared plus 4x. Or three x squared minus 5x plus 7 divided by 2x plus 1 over x minus 4. So every function that is the quotient of 2 polynomials is going to be a rational function. And the domain of a rational function is the set of real numbers for which the denominator does not equal 0, for which q of x that's singular, for which q of x does not equal 0. That is for which the denominator does not equal 0. So the most basic rational function is 1 over x. Or the most basic rational function that is not a polynomial. So that's f of x equals 1 over x. Like we did with the basic functions, we are going to make a table and have an idea of what the graph looks like. The first observation is that at 0, the function is undefined. 1 over 0 is undefined. At 1, 1 over 1 is 1. And at negative 1, 1 over negative 1 is also negative 1. At 2, 1 over 2 is 1/2. And at a negative 2, 1 over negative 2 is negative 1/2. And at 1/2, the reciprocal of 1/2 is 2. And the reciprocal of negative 1/2 is negative 2. So let's draw the graph. Okay, so the function is undefined as 0. It passes through 1, 1, and negative 1, negative 1. At 1/2, y is 2, and at 2, y is 1/2. At negative 1/2, y is negative 2, and at negative 2, y is negative 1/2. And it's going to have this property. When x gets closer and closer to 0 and remains positive, y is going to keep increasing. Like let's say 1/110 is going to be 10. 1/100 is going to be 100, and so on. So as you get closer to 0, y will keep increasing. And when x approaches infinity, that is when x gets larger and larger, like 1/10 is going to be 1/10. 1/100 is going to be 100, and so on. So when x approaches infinity, y will remain positive, but approach 0. Then we have that. When x approaches 0 from the left, y will increase in the negative direction. And when x approaches negative infinity, y will approach 0, but remain negative. But it's going to be a negative number. So these are some of the characteristics of 1/x. That this function is decreasing. It is decreasing, or let's start with the domain. We see that the function is undefined as 0, so the domain is all real numbers except 0. Or negative infinity 0, union 0 to infinity. This function is decreasing over its entire domain. In this case, the entire domain is negative infinity 0, union 0 to infinity. So we cannot say that is decreasing for all real numbers, because at 0 is undefined. If it doesn't exist at 0, we cannot tell anything about the behavior. It is discontinuous. Okay, so at 0, the graph is going to break. So it's going to approach negative infinity. Then at 0 is undefined, and then jumps to approaching infinity as x approaches 0 from the right. So this is discontinuous at x equals 0. And the range is going to be everything but 0. So any y value is an output of this function except 0. You don't have a number for a value of x for which 1/x is equal to 0. So the range is all real numbers except 0. Okay, so here are some characteristics of this function. We also have some other things. If you observe this behavior again, when x approaches infinity, y approaches 0. Or when x increases without bound, the graph gets closer and closer to the x-axis. And when y approaches 0 from the left or from the right, when x approaches 0, y either approaches infinity from the right or negative infinity from the left. So the x-axis is a horizontal asymptote. And the y-axis is a vertical asymptote. And finally, f of the opposite of x is equal to the opposite of f of x. So in that sense, f is a node function. Okay, so these are the characteristics of 1 over x. Okay, so we're going to do some transformations. That is shifts, reflections, stretches, and shrinkings. Okay, I'm going to go over example 1. That's on page 362. So yes, the graph can be translated, translated, stretched, compressed, or reflected. This example 1 on page 362. Okay, graph y equals the opposite of 2 over x. Give the domain a range and the largest open intervals of the domain over which the function is increasing or decreasing. So our function is the opposite of 2 over x, which is the same as -2 times 1 over x. So the graph of 1 over x is going to be, or was, reflected with the minus sign. We know that it was reflected across the x-axis. And it was vertically stretched by a factor of 2. So it was vertically stretched by a factor of 2. We're going to make a table to see what the graph is going to be. Doesn't look like this is going to affect the domain or the range. So still, the opposite of 2 over x is undefined as 0. So I'm not even going to write 0 because I know that the graph is going to be undefined there. And I'm going to take the other value. So we had -1/2, -1, -2, and then 1/2, 1, and 2. So 2 or -2 over -2 is 1. -2 over -1 is 2. And -2 over -1/2 is 4. -2 over 1/2 is 4. -2 over 1 is -2. And -2 over 2 is -1. So that one this one is a -4. And we're going to sketch the graph. So compared to 1 over x, the graph was reflected across the x-axis and vertically stretched by a factor of 2. Okay, so let's plot the points. We have -2, 1, -1, 2, and 1/2, 4. We have this branch. And we have 1/2, -4, 1, -2, and 2, -1. The domain and range of this function. So they were asking us for the domain and range and the largest open intervals of the domain over which the function is increasing or decreasing. Okay, so x is never going to be 0. We know that -2 over 0 is undefined. So the domain is -∞, 0, union 0 to infinity. The y value is never going to be 0, so that's going to be the range. You don't have a number x for which 1 over x is equal to 0, so the range is going to be everything but 0. And this function is increasing. So there are two intervals. I'm going to list them separately. This is increasing over -∞, 0, and 0 to infinity. Okay, next example. Let's now take the function f of x equals 3 over x minus 2. And we have the same questions as before. We're going to graph the function, determine the domain and the range, and the intervals where the function is increasing or decreasing. So if g of x is 1 over x, then f of x is going to be 3 times f of x minus 2. Okay, so the graph of 1 over x is going to be vertically stretched by a factor of 3. And it is going to be shifted 2 units to the right. Okay, so let's see. So our values were initially 0. Let's say, well, 0, this is not 0. So they were 1/2, 1 and 2. But the graph has been shifted to the right. And -1/2, -1, and -2. So this is what I'm doing. I'm subtracting 2 from every x value in the other table. So this didn't affect the domain. So -2 minus 2 is going to be, or -2 plus 2 is going to be 4. Then -1 plus 2 is 1. -1/2 plus 2 is 3/2. 1/2 plus 2 is 5/2. 1 plus 2 is 3. And 2 plus 2 is 4. The y values are going to be the same. Well, that's vertically stretched. So let's see. So we have what? 3 over 0 minus 2 is going to be -3/2. 3 over 1 minus 2 is going to be -3. And then 3/2 minus 2, let's write a note. 3/2 minus 2 is going to be 1/2. And 3 over 1/2 is going to be 6. So that one is going to be 6. And that's going to, well, that one is negative. And I'm going to delete that. 5/2 minus 2 is 1/2. 3 over 1/2 is 6. 3 minus 2 is 1. So 3 over 1 is 3. And 4 over 2 is, or 4 minus 2 is 2. So 3 over 2 is going to be 3/2. We're going to sketch the graph. And what happened here is that the graph shifted 2 units to the right. So now the vertical asymptote is going to be at 2, at x equals 2. Okay, let's plot the points. So 1 over x is undefined at x equals 0. 3 over x minus 2 is going to be undefined at x equals 2. So that's where the vertical asymptote is going to be. The graph shifted, so that's going to be the vertical asymptote. Let's plot the points. We have 0, -3/2. 1, -3, and 5, and let's see, 1, -3, and 0, and sorry, 3/2, -6. So we have this part. It wasn't shifted vertically, so the horizontal asymptote didn't change. And then it passes through 5/2, 6, 3, 3, and 4 3/2. Okay. So you can see that the vertical asymptote is x equals 2, or the line x equals 2. Is a vertical asymptote. Now in my MATLAB, you don't have to make these tables. You're going to take 1 over x as the basic function and indicate the transformations. Okay, so the line x equals 2 is a vertical asymptote. The domain is now going to be everything but 2. That's the domain. So the function is undefined at 2, that's negative infinity 2. Union 2 to infinity. The range was not affected. The range is everything but 0. And this function is decreasing over the intervals, negative infinity 2 and 2 to infinity. Okay, the next rational function that we'll study is going to be 1 over x squared. Okay, so let's consider f of x equals 1 over x squared. So this is also undefined as 0. The domain is still going to be the set of all real numbers except 0. And to sketch the graph, we're going to make a table with the same values I picked before. So that's going to be negative 2, negative 1, negative 1/2, 1/2, 1 and 2. Let's start with 1. 1 over 1 squared is 1. Negative 1 squared is 1. So 1 over negative 1 squared is also 1. 2 squared is 4. 1 over 2 squared is 1/4. And 1 over negative 2 squared is also 1/4. 1/2 is 1/4. 1 over 1/4 is 4. And 1 over negative 1/2 squared is also going to be 4. Okay, let's plot the points. Okay, we have a few points. We have negative 2 1/4, negative 1 1, and 1/2 4. We have this branch. And we have what? We have 1 1, 1/2 4, and 2 1/4. So if you notice, we have 1 over x squared. So that function can, the y values can never be negative. So as x approaches 0, f of x approaches infinity from both sides, from the left and from the right. Some of the characteristics are similar to the characteristics of 1 over x. The x-axis is a horizontal asymptote. And the y-axis is a vertical asymptote. the domain is all real numbers except 0. And the range, so 1 over x squared can never be negative, and it cannot be 0. So the range is going to be 0 to infinity, excluding 0. Anything else? This function is increasing over negative infinity to 0. And it is decreasing over 0 to infinity. And one last thing is that f is an even function. F of the opposite of x is f of x, because minus x raised to the second power is going to, or minus x squared is going to be x squared. So this is true. Thus, f is an even function. Okay, so I'm doing an example with a transformation of 1 over x squared. And I'm going to tell you how to find the asymptotes without graphing the function. So let f of x be 1 over x plus 1 squared minus 2. We are going to give the domain and range. And largest open intervals over which the function is increasing or decreasing. And we are going to graph the function. Okay, the first observation is that the graph of 1 over x squared is, so it's going to be shifted one unit to the left and 2 units down. So let's see. So we know that the graph is going to be shifted. So it's going to be shifted 1 unit to the left and 2 units downward. So anything else? So we know the vertical asymptote. And the horizontal, well, that was the horizontal asymptote and the vertical asymptote. Okay, so some points on this function. If x is -1, well, that is going to be undefined. If x is 1, or if x is 1. If x is 0, we have 1 over 1 squared. That's going to be 1 minus 2. So if x is 1, y is going to be -1. And if x is -2, we have -2 plus 1 is -1. -1 squared is 1. So 1 over 1 minus 2, we are also going to have 2 -1. And we have some other points, but at the end, I'm not going to go over all the details. On the homework, you have the transformation, so you don't need to worry about making tables. And actually, I can show you a homework problem. But let's finish this first. So now we can tell that the line, so the vertical shift, change the horizontal asymptote, and the horizontal shift change the vertical asymptote. The line x equals -1 is a horizontal asymptote. Also, the line y equals -2 is a vertical asymptote. The domain of this function is all real numbers except -1. So that's -∞, -1, union -1 to infinity. The range so y is never going to be -2 or less than that. So the range is going to be -2 to infinity. The function is increasing over -∞ to -1, and it is decreasing over -1 to infinity. Okay, but let me show you. The last part is about the asymptote, but let me show you what the homework problems look like. And no, you don't have to draw a table by hand. Okay, so let's look at that. Okay, so well, in the first one, you just need to identify the domain, but I was looking for one with a graph. Where you're doing the transformations. Well, actually, I don't even see that. Yeah, the vertical asymptote occurs when, and I'm going to talk about the asymptote, but I was looking for one with a graph. Yeah, you just need to select the appropriate characteristics. So you don't need to do any graphing. Well, you can. Well, there's something like what we did. So to obtain the graph of f, the graph of f, we have -11. We're going to stretch the graph of y equals x squared vertically by a factor of 11 and reflected across the x-axis. And that's it. So you don't need to graph anything. And to obtain the graph, it's just a multiple choice. There was a reflection, the graph is narrower, so that's going to be the vertical stretch. And yeah, you need to select the domain and range. The domain and range is everything but 0. Yeah, so the graphing is really multiple choice. And that's it. But yeah, we don't do any graphing. Yeah, the range is all negative numbers. excluding the 0. And yeah, I'm going to stop here, but you have the idea now. Yeah, so you don't do any graphing, just identify the transformations and answer the rest of the questions. Okay, so I'm going to do the last part today about asymptotes. Okay, this is on page 365. Let me find this. So that's on page 365. What happens with the asymptotes? Let P of x and Q of x define polynomial functions. Consider the rational function f of x equals P over Q written in lowest terms. That is, there are common factors, those are simplified, and real numbers A and B. So if f of x approaches infinity, or the absolute value of f of x approaches infinity as x approaches A, then the line x equals A is a vertical asymptote. So some situations of vertical asymptotes. Okay, one could be, okay, so the vertical asymptote is the line x equals A. Okay, so one situation is that the graph approaches the asymptote. If it approaches from the right, the graph is increasing from the right and decreasing from the left. And the blue line is the vertical asymptote. Another possibility could be like this. You have again the vertical asymptote. And could be that it approaches infinity as x approaches y from the left, and negative infinity as x approaches A from the right. Or it might be in the same direction, like 1 over x squared. Yeah, so it could be another example of a vertical asymptote could be like this. That it approaches negative infinity as x approaches A from the left and from the right. And then if f of x approaches B, as the absolute value of x approaches infinity, then the line y equals B is a horizontal asymptote. Okay, so in the previous examples, the line x equals A was a vertical asymptote. In a horizontal asymptote, if f of x approaches B, as the absolute value of x approaches infinity, that is, as x approaches, that could be negative infinity or infinity, then the line y equals B is a horizontal asymptote. So the graph of a function is never going to cross a vertical asymptote, but it may cross a horizontal asymptote. So one possibility could be like this. You have the line y equals B. and the graph of the function will approach B. Or the graph can actually cross a horizontal asymptote. Okay, suppose that y equals b is a horizontal asymptote, and the graph of the function could do things like this, like well, approach y equals b, but then it can cross. It can do things like that. So the next question is how to find the asymptotes. Okay, so I'm going to copy this box by parts. Okay, in the last two graphs, the line y equals b is a horizontal asymptote. Okay. Now, how to determine asymptotes? To find the asymptotes of a rational function, defined by a rational expression in lowest terms, use the following procedures. Find any vertical asymptotes by setting the denominator equal to 0 and solving for x. If a is a 0 in the denominator of the denominator, then the line x equals a is a vertical asymptote. And other asymptotes, I'm not covering slanted asymptotes, so I'm not even going to copy that. Okay, so determine any other asymptotes by consider two possibilities. I'm not going to do oblique or slant asymptotes. If the numerator has lesser degree than the denominator, then there is a horizontal asymptote, y equals 0. If both the denominator and numerator have the same degree, and you have a quotient of two polynomials, then the horizontal asymptote is going to be the quotient of the leading coefficients. And horizontal asymptotes are not covered. So these are going to be the last examples on page 375. Okay, give the equations of any vertical, horizontal, or we're not doing the oblique asymptote. That's not in the homework, and I'm not going to do it in the examples. Number 38. That's on page 375. We're looking at number 38, or number 38. That's -6 over x plus 9. Okay, so know that the numerator has degree 0. The numerator, which is -6, has degree, that's a constant, so that has degree 0, and the denominator has degree 1. That's a linear function, so it has degree 1. So let's find the vertical asymptote. Okay, to find any vertical asymptotes, find any vertical asymptotes by setting the denominator equal to 0 and solving for x. Okay, so we are going to set the denominator is x plus 9. So we're going to set x plus 9 equal to 0 and solve for x. This means that x is equal to negative 9. That's the vertical asymptote. And the horizontal asymptote. And by the way, we're not going to graph the function, we're just going to determine the asymptotes. Okay, to find the horizontal asymptote, if the numerator has lesser degree than the denominator, then there is a horizontal asymptote, y equals 0. The numerator has degree 0 and the denominator has degree 1. So the horizontal asymptote is going to be y equals 0. Because the degree of the numerator is less than the degree of the denominator. Number 43. We have the same questions. We're going to give the equations. We're going to give the equations of any asymptotes. That is of any vertical and horizontal asymptotes. So let's start with the vertical asymptotes. Okay, so we let the denominator be 0 and solve for x. We can solve this by factoring. 2x squared factors as 2x and x. And then we want the combinations to be the product of the last terms to be negative 10 and the combinations to be negative 1. So we can let x be, we can let the last terms be 5 and 2. And minus 5x plus 4x is going to be 0. So solving, 2x minus 5 equals 0. So one vertical asymptote is 5/2. And setting x plus 2 equals 0. The other vertical asymptote is x equals negative 2. Okay, these are the vertical asymptotes and the horizontal asymptote. Know that both the numerator and the denominator have the same degree for the horizontal asymptote. Okay, so both the numerator and the denominator have the same degree. Have degree 2. So the horizontal asymptote is going to be the quotient of the leading coefficients. So y equals the leading coefficient of the numerator is 1, and the leading coefficient of the denominator is 2. So it's going to be 1/2. So y equals 1/2 is the horizontal asymptote. And these two equations, x equals 5/2 and x equals negative 2, these are the vertical asymptotes. I'm going to keep them like that because they are equations of vertical lines. The solutions of the of the equation are -2 and 5/2, but x equals -2 and x equals 5/2 are equations of vertical lines. And the last one is number 46. Okay, so let's start with the vertical asymptote. If you set x squared plus 9 equals 0, you have that this has no real solution. So x squared plus 9 is always positive. So this has no real solution. If it has no real solution, if the solutions are complex, there is no vertical asymptote. And the horizontal asymptote, so both the numerator and denominator have degree 2. So the horizontal asymptote is going to be the quotient of the leading coefficients. So that is going to be the horizontal asymptote. The last part of this section is how to graph a rational function, but I'm going to cover that in the next video. Thank you for listening.